this is a summary, you might say a broad brush summary of what you'll find in that fourth phase book, that there really is a fourth phase. It's called Easy Water. And the fourth phase actually sits between ice and water. How do we know that? Well, we have a few experiments that demonstrate. The first is that we found that in order to freeze water, that you cannot go directly from water into ice. You go from water into EZ, which has a similar, not the same, similar kind of molecular structure as ice. They both have this hexagonal motif to them. We found that it's obligatory to go through this phase, the EZ phase, in order to go from water to ice. And if you melt ice, it's necessary, obligatory to go from ice to EZ water, EZ, in order to get to ordinary liquid water. So this is a necessary condition, which actually clears up so many anomalies, but I don't have time to describe. So the way it looks on a molecular scale is, so remember the EZ structure has these sheets of hexagons. So here's one sheet and here's another sheet. And the sheets are actually held together electrostatically because the sheets all have the same structure, but they're shifted from one another so that on one sheet, the positive charge matches up with the negative. You might have oxygen here and hydrogen here, and they stick together. And again, they stick together, and so on and so forth. So that's the EZ structure. Now, if you add protons to it, what happens is that the protons will then gather in between these two negative charges. And what we found is what they'll do is they'll flip the molecule or shift the upper one toward the left, as you see here, or the lower one toward the right. And then you get the structure of ice. So you, with the addition of protons, you go from EZ water to ice. And notice that because the protons are stuck in between, these two planes are separated more than they are here. So this is condensed. This is very dense kind of water, and we could indeed confirm the high density of EZ water. But once ice forms, the planes are shifted apart from one another, and so it's less dense. And that's the reason why ice floats, because it's less dense than the EZ water that just preceded it. And luckily for us, the issue that ice floats is really important, because if ice grew from the bottom, if dense enough, there would be a problem for any and all fish, which could get excluded from the water, and you can imagine the consequences. So I just want to show once more what actually happens, because ice is pretty important for weather. So we start with EZ sitting here and positive charges. And if you have an increase in EZ, which will be accompanied by an increase of positive charges, because you get more negative here, you get more positive here. The two simply separate. And when you get to the point where there are enough of these positive charges eager to enter and press on toward the high negativity that you see here, they'll rush in to neutralize that negativity. And as they do, that will constitute the formation of ice, which is EZ plus protons. That's the way it works. That's the way we surmise that the ice formation occurs. Now, we have evidence to test for this proton rush, and we use a thermoelectric cooler in a chamber where we have EZ sitting here, EZ water, and we put a pH sensitive dye in here, which changes color depending on the pH. And so what happens is the situation, the cooling plate is here, and eventually this is going to turn into ice. And so when it turns into ice, you can see the red color of the ice and the green color of the water. And the red color means, according to the color code, means low pH. And so you can see that there have been, this region of ice now contains many protons. And the area of water, on the other hand, is a green color, which is high pH, which is deficient in protons. So you can see that what's gone on is that the protons have apparently migrated from the water to the ice, confirming this proton rush that I was talking about. Anyway, the bottom line is that ice formation involves protons. EZ plus protons equal ice. And this is well articulated in the book that I mentioned, and as is all the evidence in favor of it. Now, what about the melting of ice? So I mentioned that the melting of ice involves passing through, you go from ice to EZ water. So when ice melts, we ought to be able to detect the presence of EZ water. The ice melts and it goes into EZ, and the EZ eventually goes into H2O. So if we can catch the ice just as it's melting, we ought to be able to detect easy water. That's what we found, and we published a paper on it. And what this shows here is 4 different examples of absorption spectra. That is the absorbance versus wavelength in each of these 4 cases. And we looked at the water just as the ice was melting. And what we found is an absorbance peak at 270 nanometer wavelength. And it occurred consistently in each of the different kinds of water. This is deionized water, boiled, deionized, degassed, deionized, et cetera, et cetera. It doesn't matter what water you use, the result is the same. It always shows a peak at 270 nanometers. 270 nanometers is characteristic of easy water. It's the one signature character. So indeed, it's true that just melted water samples show that the ice turns into EZ. So here we return to the initial slide in this series, putting the EZ in between the ice and the water. The EZ is definitely in between the ice and the water, giving rise to these beautiful images.